So we're going to talk about integrated rate laws. We were looking at rate of reaction as a function of concentration of reactant, and that is useful, but what is more useful is to be able to predict the concentration of a reactant at a certain time. And so in order to do that, we take those rate laws and we integrate them. The good thing is they did that for us, so we don't have to do calculus. Okay. The form of the law, rate law, will depend, of course, on the order of the reaction. Okay, so if we look at a simple decomposition reaction, these are nice because there's only one reactant. So decomposition reaction, the reactant decomposes into some products. We don't care what they are. We're going to look at a first order reaction. The change in the concentration of A over time with a negative, because this is the reactant, wait a minute. I skipped a line. Okay. Sorry. Okay, so our rate law here, because it's a first order rate law, the rate is equal to a constant times the concentration of A. We also know that the rate is equal to the rate of change of A, but negative, right? Because A is going down, and so its rate of change is decreasing, is negative, but the rate of the reaction has to be positive. So we know that these two things are true. They're both equal to the rate, and so we can put them together. So that's what's called the differential rate law. Not really so useful. That's going to be one of those nights. No, we don't need parking permits. So if we take that and we integrate it, doing calculus, and for those of you that like calculus, you can play around with that on your own. We get this form. We can express it this way or that way. So the natural log of the concentration of A at time t is equal to negative times the rate constant times that times time t, times the time, yes, plus the natural log of the original concentration of A. We can also look at it in this form where we're looking at the ratio. What's nice about this form, though, is it takes the form of a line. Y is equal to mx plus b. So the natural log of A at time 0 is the y-intercept. The slope is equal to negative k. And we're graphing natural log of the concentration as a function of time. So this is y, the y value, and time is the x value. And so for first order reaction, when we do this graph, we're going to get a straight line. The slope is negative, but the rate constant is positive. Yes?
Time is delta T, like the final initial, or is it just?
So that's a good question. Is the time here delta T? Well, if it ends up being the same if you consider the initial time to be 0. But it's the time now after it started. So it would be like, maybe 10 seconds. It wouldn't be 3 o'clock. Yeah. Any other questions?
And the T will usually be given to you in the problem, right?
So we've got all these different variables. Sometimes they'll give you the T, and they'll ask you for concentration. Sometimes they'll give you the T and the concentration and ask you for the rate constant. Sometimes they'll give you the rate constant and the concentration and ask you for the time. So just any possible permutation, we'll see it somewhere.
Okay.
Yeah, good question. Okay, so graphing is one way to determine the order of a reaction. So here we've got this reaction, SO2Cl2 is decomposing to form SO2 and Cl2. So they're monitoring the concentration of the reactant at a fixed temperature as a function of time. So here we have the time, they're measuring it every 100 seconds. Here's the concentration, and this goes on for 1,500 seconds. And the statement here is show that the reaction is first order and determine the rate constant. So we can't use our, well, what happens when the thing doubles, right? Because we don't have rates at these times. We don't know what the rate is, right? So to figure out if this is first order, we need to do a first order integrated rate law plot. So we're going to take the natural log of the concentration of SO2, Cl2 at time t, and we're going to plot that versus the time. And I can't remember what's coming next in the slides. It's exciting. There we go. I was hoping it was that. Oh, actually, let's go back here just a minute. So how do you get that information? Well, the time is fine. We're just going to use that normally. But here we have the concentration, and we're going to have to take the natural log of all those concentrations. Okay. And one thing we'll be doing in this class is we're going to learn how to get Excel to do a lot of grunt work for us. Okay. This is a lot of repetition of the same thing, taking the natural log of a number. That's something that computers are really good at. And so when we need to do stuff like this in lab, we'll make the computer do that. So here, by the magic of PowerPoint, we have our graph, right? So natural log of the concentration versus time. And lo and behold, it forms this nice straight line. We use linear regression, done by the computer or your calculator, to determine the best fit line for those points, okay? So our integrated rate law, let's remember, was the natural log of the concentration is equal to negative the rate constant times time plus the natural log of the original concentration. So this is our slope, and this is the intercept. So y equals mx plus b. The slope is negative 0.000290. So m equals negative 0.000290. The relationship between the slope and k, m is equal to negative k. So that means that this is equal to negative k. And we can cancel out those negative signs, right? So then the rate constant is equal to 0.000290. Rate constants have units. So we should put a unit on this. Now, you can memorize the rate constant units. I can never remember them. And so I'm just thinking, well, the rate is molarity per second, and that's equal to the rate constant times the concentration. That's supposed to be the same kind of an M. So I can tell from that that the unit here is per second. We have demonstrated that this is a first order reaction because this graph gave us a straight line. If it was zero order or second order, it would have a curve to it. Any questions? Yeah.
Is that a T at the end of the graph?
This is a T, yes. That's a T. It's not a very good T, is it? Let's make it a little better. Sometimes we'll just call this the concentration, and just specify that this was the initial concentration to avoid all those subscripts all over the place. Any other questions? So this is saying, okay, use the graph in the best fitting line to predict the concentration of SO2Cl2 at 1900 seconds. Our data doesn't go out that far, but we could predict the concentration based on that line equation. So we're trying to find this concentration, and 1900 seconds is our time. So I can take the equation for the line and put the actual time in for t. So 1900. And then that's minus 2.30. And I can calculate that. And that gives me negative 2.851. And that's y, and y is equal to the natural log of the concentration we want. Yeah, so we need to undo this logarithm, right? So the opposite of natural log is e to the x. So we'll take e to the x of both sides. So I get e to the negative 2.851 is equal to e to the negative log of the concentration. Well, those guys cancel out. And so this is just equal to the concentration then. So I've got that number in my calculator. I'm going to do e to the x. And I get a result of 0.057786505. That's a concentration, so what should the units be? Molarity, moles per liter. Now that's a ridiculous number of digits, right? What seems like it would be a reasonable number? Like 3 sig figs? Just, this is not following sig fig rules because sig fig rules with logarithms get a little weird. But this had 3 sig figs. This one, understanding how the measurements are made, we're like, yeah, that one probably has 3, and that one's got 3. So let's report this to 3 significant figures. We'll round this to 0.0578 molar. I think it's a good idea when you're doing a problem to always write down, not necessarily all of the digits, but a few more than you think you're going to need. In case you need to come back and use that number in a calculation, then you don't have to redo it. Any questions? Here's another example. Cyclopropane rearranges to form propene in the gas state. The reaction is first order in cyclopropane and has a measured rate constant of 3.36 times 10 to the minus 5 per second at 720 Kelvin. If the initial cyclopropane concentration is 0.0445 molar, what will the cyclopropane concentration be after 235.0 minutes? Now that's just like a classic word problem there, right? Word problems are harder for some people than for others. It's not intelligence. It's just how your mind works, right? Some people understand politics. I do not. And it's just not even that very interesting to me. And some people can really appreciate poetry, and I like some poems, but most of them, So, we all have our things that we're naturally good at. But even if you're not naturally good at word problems, we call them story problems when I was a kid, you can get better at them, right? So that's what we're going to do. We're going to get better. Always read the question all the way through. And then the numbers are almost always going to be important. So I'm just going to go in here and highlight the numbers with their units so I can see what we've got. So let's pull those numbers out and try to label them. So it says this is the measured rate constant. So the symbol for the rate constant is lowercase k. So that is 3.36 times 10 to the minus 5, s to the minus 1. And then we've got a temperature of 720 K. Now, I've done this one before. I know that we don't actually need that, but you probably don't know that. So let's write that down. The temperature is 720 Kelvin. Then it says the initial cyclopropane concentration is this much. So we probably can't just spit out the chemical formula for cyclopropane off the tops of our heads, and writing out cyclopropane is just too many letters. So let's just call it A, right? So we're just going to, represent compounds a lot with letters. So that's the concentration of the reactant, and we can tell ourselves that's what it is if we want to. So we've got A going to products. And to indicate that that is the initial concentration, we're going to put a subscript 0 after it. That is the concentration at time 0 at the beginning. And then we have 235 minutes. And that's time, right? Okay, so that's what we were given. What are we trying to find? Yeah, we're trying to find the concentration of the cyclopropane at this new time. So we're going to call that, let's see. So this is what we're trying to find, and we're just going to call that A. So that is the concentration at whatever time we are looking at. A 0 is when time was at the 0 at the beginning. Now, the other thing that is helpful here is they tell us that this is first order. So now we can write the rate law, but the rate law itself isn't going to help us very much. What we want is the integrated rate law, because that allows us to look at the two different time points. So the first order integrated rate law is the natural log of A is equal to negative K times T plus the natural log of the initial concentration. So we were given K, we're given the initial concentration, we're given T, we're given all the variables on the right side, and we're trying to find A. I think I mentioned last week, unlike Chem 1A where I always recommend that you rearrange the equation and then plug the numbers in, our equations here are a little more complicated. And so it's usually best just to plug the numbers in and let your calculator do some work for you. So negative times the rate constant and that's s to the minus 1. And that's times time. Do we have an issue here with units? Yeah. So this was given in minutes. All of these calculations are done in seconds. So we need to convert this to minutes, the minutes to seconds. So there are 60 seconds per 1 minute. So I can take that to 35 and multiply by 60. And this is 14100 seconds. And that would be the last sig fig. Oops. So you probably should call that 1.410 times 10 to the 4 seconds. Plus the natural log of the initial concentration. Initial concentration was 0.0445 molar. So we can calculate that side. Negative 3.36 EE minus 5. You should get your calculator out and make sure that it is cooperating. Times 1.410 EE 4. And then I pressed equals, and then I'm adding the natural log of 0.0445. Did you get your calculator to tell you negative 3.586026? Okay, good. If we're going to write that down, we want to write down some extra digits. But now I know that the natural log of A is equal to that, and so I can say that A is equal to E to the negative 3.586026. I have the whole number in my calculator. So I'm not going to type it back in, I'm just going to use it from the display. So on mine, I press the E to the box button, and then I go up to select my previous value, press enter again. And the concentration there is going to be molarity or moles per meter. How the units work out is a little harder to see in these equations, but we also don't go using all kinds of different units. Molarity is always what we're going to use for concentration, moles per liter. The time is always going to be in seconds. The rate constant is always going to have whatever order it is, the appropriate units. Any questions? Is that a reasonable concentration? Well, how could we tell? It started at 0.0445. Is it going up or down? It should be getting smaller. It got smaller, so we have no reason to be suspicious of that. But if we got like 2.7, we'd say, wait a minute, I did something wrong. Or if you get a negative concentration, that's never good. Okay, so let's look at the second order reaction. So here the rate would be equal to a constant times the concentration, that reactant squared. The rate is still equal to negative delta A over delta T. So we can put those together to get the differential rate log. You integrate that, and you get this guy. So this is second order. And we're going to write this in the form of an equation for a straight line. So 1 over A at the time of interest, that's our y variable. K is going to be our slope. T again is the time, the x variable, and the y-intercept will be 1 over the initial concentration. So we're going to graph 1 over the concentration versus time. We're going to get a linear plot with a positive slope this time. So consider the equation for the decomposition of NO2. Concentration of NO2 is monitored at a fixed temperature as a function of time. We have the temperature that we had before. These equations don't have temperature in them. So why do they keep talking about the temperature? They talk about the temperature, and they'll sometimes give you a temperature because the rate of a reaction changes with temperature. And so they're just kind of being thorough, and they're saying, well, this was the rate constant at this temperature, and the things that we're doing are at the same temperature, meaning we don't have to do anything with the temperature. So don't feel like just because they gave you a number, you have to use it. So here it's talking about a fixed temperature. Temperature isn't changing. So they tabulated the data, and they're saying, show by graphical analysis that the reaction is not first order, and that it is second order, and determine the rate constant. So here we have 0 to 1,000 seconds and the concentration of our reactant in moles per liter. So to show that it's not first order, we're going to do a first order graph and see that it's not linear. To show that it is second order, we're going to do the second order graph and see that it gives us a straight line. Okay, so here's what we get. If you don't actually draw the line and kind of look at it casually, you're like, well, it kind of looks like a line. But then when you actually draw the line on there, you see that it's above at the beginning and the end, and it's below in the middle. And we can't just ignore that. That is a curve, okay? Sometimes your data has a lot of noise in it. It's kind of messy. But then the data points will be on other sides all the way down. They'll be scattered somewhat randomly instead of below in the middle and above on both ends. So here's our second order plot, 1 over the concentration versus time. Computer gives us the equation for the line y equals 0.255x plus 100. So what's the rate constant? 0.255. So this is our slope. So our rate constant, K, is equal to 0.255. And then the units, I'm just going to think back to, okay, the rate is in moles per liter times the rate constant times, molarity per second, and the rate constant squared. So my units here are going to be molarity to the minus 1, S to the minus 1. Any questions? Finding an equation that gives us linear graphs is really, really useful, because we can use linear regression and identify the best fit line. Nowadays we've got computers that can fit complicated curves and things. But when I was in college, we drew these graphs out on paper, on graph paper, and you took your ruler and you drew the best line you could, and then you found 2 points and you calculated the slope like that. There wasn't really anything else you could do. right? But it worked. So we're always looking for linear graphs. Any questions? You guys make me feel ancient. That's okay.
I remember using graph paper in high school.
Well, they do make you use graph paper, yeah. Okay, so now let's use the graph in the best fitting line to predict the concentration of NO2 at 2,000 seconds. When we've got the equation for the line here, this is actually a fairly simple process, right? Because the time here is 2,000 seconds, and that's the x variable. So y is equal to, the y variable is equal to 1 over the concentration, and that is equal to 0.255. Well, let's do it this way. Molarity seconds times the 2,000 seconds plus 100. So we got, turn the calculator on, 0.255 times 2,000 plus 100. So 1 over the concentration is equal to 610. If we look at the units here, this second cancels with this one. This ends up having units of per molarity, and this one also would have units of per molarity. So what we need to do is upside down this, right? Invert it. And you can do that on your calculator. Mine has an X to the box button, and so I can put in answer to the -1, and it gives me the stupid fraction. I have to tell it, no, I don't want you to show me 1 over 610. I could have done that. There's a button, F to D.
Mine's S to D.
So 0.016393. And again, I'm probably going to report this to 3 significant figures. And so that would
Sorry, so how did you go from the 610 to the decimal there?
That's a great question. So what I did is I used the X to the box button on my calculator. So I had this 610 in the display, and this is the TI-36X Pro. I had this in the display from doing this calculation. When I press this, it takes the answer and is asking me what power I want to raise it to. So then I typed in that negative sign, not the subtraction sign, and the 1, and pressed enter. Other calculators might have a 1 over x or an x to the -1 button. You can also do 1 divided by, go up and pick up that number and press equals. So this is a good time to learn some of these more sophisticated things on your calculator because they're going to be really useful in this class. Any other questions?
What was the units that will end up with that?
So we'll end up with concentration units of molarity. And, looking at the graph, it's not obvious what the units on the y-intercept are. So as I started putting units into the equation, I thought, well, maybe that wasn't actually a very good idea.
So the molarity below the 100 won't cancel with the...
So the units of this side are going to be per molarity.
okay, got it.
Yeah. So this would have units of over molarity, and then when you invert it, you get molarity. So all the units do work out. Okay. I'm not going to make you prove that or anything. Again, if we're just consistent, use seconds and molarity, it's going to come out just fine. Any other questions?
So in the exam or something like that, do we have to put in the units all throughout, like while we were doing the math as well, or just the final?
That's a good question. So, exams will be partially multiple choice and partially show your work. So in the multiple choice ones, do whatever you want, right? But in the show your work ones, do we need to show all the units in those calculations? I don't think you do, okay? Because with logarithms and stuff, it's not very clear sometimes. You need to be able to end up with the right units at the end. If you're calculating a concentration, like some of those problems on the worksheet, there you definitely should show your units, and don't write capital M, write moles per liter, because otherwise, people start dividing molarity by moles and things get funky, right? So we want to watch out for that. But here, the molarity is not being changed into something else, it's just a molarity, and so then capital M's okay. Any other questions? Okay, what about zero order? Well, following this same process, for zero order, the rate is equal to K times the concentration to the 0 power, which is just K. The rate is always still equal to negative change in concentration over change in time. So we get the change in concentration over change in time is equal to K, negative K. And so then when we do the integrated rate law, we get the concentration of A at time t is equal to negative KT plus the concentration at 0. So here, a plot of concentration versus time is linear. And these are the kinds of plots we were looking at before, concentration versus time. The slope of the line is related to the rate. And so here it's constant. So the slope is equal to negative K. So we're going to talk about half-lives. And half-life here is the same quantity that we talk about when we talk about radioactivity. So half-life, or T1 half, is the time needed for the concentration to fall to 1/2 of its initial value. Okay, so if the initial concentration is 0.5 molar and T1 half is 50 seconds, what will the concentration be after 50 seconds? It'll be half, right? So after one half-life, the concentration is cut in half. So half of 0.5 is 0.25. What about after 100 seconds? Well, a good guess would be 0.125. The thing is, the half-life expression is different for different reaction orders. So for a zero order reaction, then it would just continue to be 50 seconds, and after 100 seconds, it would be cut down to 0.125. But if it's a first or second order, it's not going to do that. We can calculate what the half-life is from the integrated rate law. So here, they just used a rearranged form of that so that we've got concentration at time t and concentration initial. So At half-life, we know that the concentration now is 1/2 of the original concentration. So we have the natural log of 1/2 A0 divided by A0. Because this concentration in the numerator is 1/2 of A0. So I just plug this in for that. And this is going to be equal to negative KT, because that's what the rate law says. Well, here in the parentheses, the concentrations cancel out. So now I have the natural log of 1/2 is equal, oh yeah, we call this time T1/2 now. It's equal to negative K times T1/2. Well, what's the natural log of 0.5? It's negative 0.693, and that's how they usually report it. It's negative KT1/2. So we can solve that equation for T1/2, and T1/2 is going to equal 0.693 divided by the rate constant. Any questions? So here, the half-life is going to depend on the concentration. So I misspoke earlier when I said that it was the half-life was constant for zero order. It's not the zero order, it's the first order. So when we have a first order reaction, the half-life is independent of the starting concentration. So regardless of how much stuff you have, the half-life is going to be the same. And the half-life is going to be constant as the reaction proceeds because it doesn't depend on the concentration. So if we start with 1 molar stuff at time 0, after 1 half-life, we're at 0.5. And after 2 half-lives, we're at 0.25. And after 3 half-lives, we're at 0.125. And it just keeps cutting in half. You don't get to 0 after 2 half-lives because it slows down. So the images here depict the first order reaction A going to B at various times during the reaction process. The black circles represent the reactant A and the red circles represent the product B. What's the half-life of the reaction? Well, here we have time 0. And so we can count how many dots are in the box, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 particles per box. What's going to be true at the half-life? We're going to have 5. We'll have 5 black ones, and the ones that reacted will turn into 5 red circles, right? No, that one's not right. This one's, no. There we go. 5 black circles and 5 red circles. So this must be the half-life. That make sense? There's a lot of times where you can, if you're stuck on a problem, you can help yourself through it by remembering, well, what does half-life mean again? Oh, it's the time when the concentration is half of what it was initially. So then you can mess around with things. First order reaction A to B has a half-life of 25 minutes. If the initial concentration of A is 0.3 molar, what is the concentration of B after 50 minutes? Do not use a calculator to solve this problem. So we start with 0.300, and after one half-life, that gets cut in half, right? So one half-life passes, now we've got 0.150 molar. So one half-life is 25 minutes. So this is 50 minutes, so we need to go another 25 minutes, another half-life. So what's the concentration going to be? Yeah, it's going to get cut in half again. Every half-life, it gets cut in half. That's true for first-order reactions.
So in this case, would you select B since it's the closest?
That's a good question. Did I do something wrong?
No, because that's the concentration of A, and we're finding the concentration of B, because A is equal to B.
Bless you. Thank
It
you.
took me a few seconds to figure it out.
Yeah, I don't remember there being an issue like that in these slides. It's asking what the concentration of B is. Well, so this is the concentration of A. So how much A reacted? So we started with 0.3, and now we've got 0.075. So how much reacted is the difference between those? So 0.225 molar of A reacted. In this equation, we get 1B for every A. So we can multiply by 1 mole of B for every 1 mole of A, and that's going to be the same, right? 0.225 molar B. And a question like that is entirely fair in Chem 1B. Caught me off guard too. So I don't look at the slides before lecture to make it more exciting for myself. Any questions? First order reaction has a half-life of 26.4 seconds. How long does it take for the concentration of the reactant in the reaction to fall to 1/8 of its initial value? Well, we could trot out the integrated rate law, but 1/8 is a nice fraction, yeah? So at the beginning we had 1, and then we have 1/2, and then we have 1/4, and then we have 1/8. Every half-life, it gets cut in half. So there's 1, 2, 3 half-lives, so 3 times the half-life. Or 79.2 seconds. Any questions? Second order integrated rate law given here. Again, let's calculate an equation for T1/2. So again, we know that at the half-life, the concentration is 1/2 of what it started with. So we've got 1/1/2 A0 is equal to K T1/2 plus 1/A0. Well, this is kind of messy here. When we have a fraction in the denominator, what do we do to pull it out? We flip it around and it goes in the numerator. So this is equal to 2/A0. So I can subtract this from both sides. I'm going to get 2/A0 minus 1/A0 is equal to KT 1/2. Well, thankfully, that has a common denominator, right? So that's just equal to 1/A0. So T1/2 will be equal to 1 over the rate constant times the initial concentration. In the second order reaction, the half-life depends on the initial concentration. Lower initial concentration gives you a longer half-life. And the half-life gets longer as the reaction proceeds. For the zero order, we've got our integrated rate law asking what's T1/2. So again, I'm going to plug in 1/2 A0 where we have a T. So if I subtract A0, that should be 1/2. Half of A minus A is going to give us negative 1/2 A0. And that's equal to negative K T1/2. So we can get rid of the negative signs. And so T1/2 is going to equal to A0 over 2 times the rate constant. My A's are starting to look like deltas. So here, half-life also depends on the initial concentration, but if the initial concentration decreases, the half-life gets shorter. And as the reaction proceeds, the half-life gets shorter and shorter. First order, it stays the same. Okay, this is a super useful table. This summarizes all of this stuff, right? So, I often see people taking pictures of the screen. You can do that, but you can also go to the PowerPoint slides on Canvas, pull it up on your phone, take a nice screenshot, and get a really good picture of it. This is a useful thing to have handy when you're doing your work. Shows what the graphs are, what the units are, all kinds of good stuff. So another conceptual problem. Did you have a question?
Which of the equations will we have to use on the test?
That's a good question. Which of the equations will you be given on the exam? If I remember correctly, I think I give you most of these.
Thank you.
Yeah. Because personally, I have trouble remembering them, right? So my feeling is if I don't remember them, I shouldn't expect students to remember them either. But we need to know how to use them, right? That's the important thing. Okay, decomposition with a rate that is observed to slow down as the reaction proceeds has a half-life that depends on the initial concentration of the reactant. What statement is most likely true? A plot of the natural log of concentration as a function of time is linear. The half-life of the reaction increases as the initial concentration increases. A doubling of the initial concentration of the reactant results in a quadrupling of the rate. This is pulling a bunch of things together. So our choices here are describing different rate orders, right? So natural log versus time being linear. Which one was that? First order. Okay, so we see down here, first order is the natural log. So A is a first order reaction. The half-life increases as the initial concentration increases. You're like, I'm going to have to think about that one. Let's look at this one. Doubling the initial concentration quadruples the rate. What order is that one? Second. So it's a good guess that this one's the 0, right? So this one is saying that the rate slows down as the reaction proceeds, and the half-life depends on the initial concentration. Well, what do we know about a zero-order reaction? Does the rate change? No, the rate's the same. So this can't be a can't be zero order, because the rate slows down as the reaction goes. So it's not B. And the half-life depends on the initial concentration. It's not saying how it depends, but it's saying it depends on. Well, that first order one is the one that does not depend on the concentration. And if we don't remember that, we can go back to our handy table here. Let's read this one. So here, this half-life depends on concentration. This half-life does not depend on concentration. This one does. So we eliminated the 0 because the rate wasn't changing, and we were able to eliminate this one because the half-life doesn't change.